Good morning. I'm Tony Freeman from JPL. I head up what we call our Innovation Foundry. It's our innovation hub. I'm here to talk about a lot of the work my colleagues are doing on CubeSats and nanosats. And we started this in about 2012. So we're very well known, we hope, for our flagship missions to explore the solar system, the Mars Rovers, the Voyagers, etc. But more recently, we've been engaged in the CubeSat nanosat world that arose from a KISS workshop, Tech Institute for Space Studies. You can find it online, I believe. It's at Caltech. And there we brought in some of the CubeSat community, Jordi Kutswari from San Luis Obispo, for example. And we said, what would it take to get CubeSats out into the deep space world? And they said, we need a lot of help. There's a lot of radiation hardening, a lot of communication protocols that we need to solve. And so that's what we embarked on. For this talk, we'll talk about those activities. The first one that we put together was called a Pathfinder named Inspire. And this is the first pair of CubeSats built deliberately for operations in deep space. They are to test out a cross-communication link and communication back to Earth through the deep space networks that we operate at NASA. They haven't launched yet. That's one of the problems in deep space CubeSats, is there aren't that many rides into deep space that go beyond Earth orbit. So they've been shelved for about 2 years now. And they will probably launch on the Earth-Moon 1 launch of SLS, which I think you'll hear about later on this week. But those spurred us to develop the two Mako CubeSats. These will fly with InSight, which is our next Mars lander, in May of 2018. They make their way independently to Mars, so they have propulsion to do trajectory adjustments. They have communication relays. In fact, that's their primary purpose, is to serve as a communication relay from the lander back to Earth. The landing event itself is out of sight of Earth, direct line of sight. So we need a way to get that data back to find out what happens to this lander as it enters the Martian atmosphere and executes its landing sequence. So these two CubeSats are really just a communications relay to do an engineering function. But of course we realized that you could put science instruments on CubeSats, and so we put quite a lot of effort into that, as have other areas of NASA, including NASA's Earth Science Technology Office. So I highlighted a few of the instruments that NASA has been working on that will go into future CubeSat missions. One is the HARC imaging polarimeter. Another is the RainCube radar that we developed that we're flying later this year. The lunar flashlight near-infrared laser, which is a LiDAR system really that goes onto a CubeSat. We have a Dyson spectrometer that's a 1.5 meter volume. It's near-infrared, spanning the range of about 0.4 to 1 micron. Our colleagues at Goddard have developed an infrared spectrometer to fly on a lunar ice cube. It will be the first cryo-cooled CubeSat instrument when it flies. And then we've also been developing things like mass spectrometers, which we've been able to miniaturize, and if we can fly through an atmosphere, we're able to sample the atmosphere with that. A few years ago, Selva and Kresge published a paper. I think they were both at MIT at the time, and they went through a list of instruments that they felt were feasible, infeasible, or problematic to put on CubeSats. And you can see that they had about a third of the list was felt to be feasible. This is 5 years ago. A third, roughly, were felt to be infeasible and completely impossible, and a third were felt to be problematic. Since then, the community, and I don't just mean JPL, I mean the wider community, has made significant progress on all of these, to the point where I think it's possible to say that all of them are feasible. That includes synthetic aperture radars. A couple of groups are working on CubeSat-sized synthetic aperture radars. It includes LiDARs. It includes altimeters. It includes some really quite high science grade instruments. They're never going to have huge apertures, so you require a massive aperture to do your job, like a telescope. James Webb Space Telescope will never be flown in the CubeSat version. However, you'll see later on that we can fly smaller telescopes to do very specific jobs. The mass spectrometer is core to what we call Cupid's arrow. Christophe Sautin, one of my colleagues at JPL, is the PI for this. I'm the co-investigator. And this is a mission that we sized as, it's a smallsat mission, but it uses CubeSat technologies. And it's a straight shot from Earth to Venus. It dips through the atmosphere, so it's an atmospheric skimmer, and it grabs a sample at an altitude below what's called the homopause, where it's representative of the gas mixture as Venus formed in its early days of the solar system. So if you sample those gases, argon, krypton, neon, etc., and their isotope ratios, you can tell where exactly in the solar system Venus formed and something about its history since that time. We also have 3 others that were involved in it. NASA funded 12 altogether at different centers. We're involved in 3 more. One is the Jupiter Magnetosphere Boundary Explorer. So the idea there is a small set gets dropped off with magnetometers and explores the magnetosphere environment. We have a similar thing for Uranus and Phobos and Deimos CubeSat Explorer that we're also building called Chariot. The Europa Clipper mission is still carrying room for several CubeSats that have been under study for a couple of years now. And the idea there is that they would be able to approach Europa at a closer distance than the primary spacecraft, perhaps fly through one of the plumes that has been identified by the Cassini mission and sample the atmosphere. I mentioned this. This is with Sarah Seeger at MIT, and it's a single star Kepler. So Kepler looked at planetary transitions for multiple stars. This CubeSat telescope looks at one star at a time and determines the transit. How can it do that? The pointing is the problem, and the pointing of the CubeSat itself is about half a degree, not atypical these days for CubeSats. But we have a fine pointing mirror that manages less than 1 micro arc second to stay on target to look at a single star. We use CubeSat technology to design the Mars helicopter. Obviously not the rotors, but the solar panels on the top. High-resolution camera is a CubeSat-style camera. The avionics and the radio are CubeSat-style avionics. We have autonomy that we can test out with CubeSats. And we have batteries and an insulator that are, again, CubeSat-style technologies. So the aim with this is to fly it with the next Mars Rover, which is currently still called Mars 2020, and have a helicopter on Mars. The lifetime of operations is about 3 minutes. It's sized for 6, but in that 3 minutes, it can survey an area which is 6 times broader than the rover can look at from its single mast-based optical system. We also have, with aerospace, a look at some entry, descent, and landing systems that are smallsat and CubeSat based. This one's called Mars Drop. And the idea here is, on several of our Mars missions, we've filled up the surface mass with ballast. And if instead we could fill it with multiple smallsats, we could actually have a distributed array with about 1 kilo's worth of instrumentation distributed across the surface. We've been developing other technologies that are critical for CubeSats, things like a deep space transponder, the IRIS transponder, our deployable reflector antenna, which is a 1/2 meter Ka band antenna. We're working on microelectric propulsion. We're working on onboard data reduction. We flew one on the IPEX experiment. And we've also been working on the deep space communication protocols that we need to communicate with a large number of CubeSats in a single antenna field of view. We've done some conceptual design work. I won't say it's gone beyond that. For deep space PPOD. PPOD is the standard deployer for LEO-based CubeSats. We think there's a need for one to carry on all future deep space missions that would be standardized, that would allow multiple players to enter into the deep space exploration arena, and if we can get this developed even further, we'd be a lot happier. Other missions you'll hear about maybe later this week, lunar flashlight that we're partnered with Marshall on. This goes into lunar orbit and shines a laser into the dark corners, permanently dark corners of the moon to see if there's water, ice on the surface. Near asteroid scout, which I know you'll hear about in one of the talks, is joint with Marshall Space Flight Center, and it uses a solar sail to maneuver itself to a near-Earth asteroid, and then a camera based on the camera we flew on our OCO mission to get close-up images. We are very happy with the SLS, which is NASA's new launch vehicle, because they've happily provided space for CubeSats on the first launch of that launch vehicle and also the second. And there are several CubeSats, I think 13 altogether. I've highlighted a few of them in this slide. But they represent, with some of them having science instruments, the first science school that we've ever sent to another body. So that's a big deal. I know my colleague Roger was hoping to do the same thing to an asteroid system. But this is still on the books. It looks like we're going to have either a late 18 or early 19 launch, and 13 CubeSats all doing different things at the moon. I wanted to highlight this heliophysics mission. JPL doesn't do a lot of heliophysics, but this one has particular significance. We proposed it recently to a NASA call, and it's a constellation of CubeSats, each with an HF radio receiver and antenna on it, and they form a synthetic aperture to look at coronal mass ejections. So coronal mass ejections cause RF whistlers that are impossible to see from Earth because of the ionosphere. So we get above the ionosphere in GEO, we can examine these coronal mass ejections, and with a synthetic aperture actually resolve where they come from and how they evolve over time. So this is would be a very nice first. It's what we call decadal survey class science. We recommend it highly by the National Academy. So it's something that essentially takes a radio astronomy array from the Earth's surface up into space to achieve the same functionality. So in summary, we have what we think is a healthy portfolio of what we also think are science-driven smallsat and CubeSat flight projects. It's very great to be involved in. We have a full pipeline of new mission concepts coming up. Lots of ideas being generated all the time. And some of them are captured on our website at jpl.nasa.gov/CubeSat. So with that, I'll take any questions.
Okay, so any questions? Please ask for a microphone. Right, first.
Okay. The organization. So, do you have a sort of person that, or an entity that organizes the whole CubeSat project, or it's mostly project-based, or someone proposes something, and then if it goes on, it's fine. So, is there any global umbrella under which the sort of directorate for CubeSats or something like that?
Yes, there is. It's very informal. So In late 2012, I formed something I call the CubeSat Kitchen Cabinet, and it represents a group of program managers at roughly similar level to myself, who can influence our CubeSat smallsat program in astrophysics, earth science, and planetary science. And I think there's about 8 of us involved in that. And we steer the technology investments. I own something called Team X, which some of you have heard of. So we instantiated a Team XC, which is the CubeSat flavor of Team X, so we can formulate these things fast. And between the 8 or so of us, we've managed to put this program together. But it's not, it's what we call a grassroots thing rather than a top-down position.
Another question out there?
Jimmy Hoffman, very nice talk, thank you. I'm just wondering, are you guys planning using commercial components for these advanced CubeSat missions, or are you going to be space qualified flight heritage components?
I should have mentioned that, and yes, in fact, we do. So on Marco, we use a VACO propulsion system. We use Blue Canyon for attitude control, and some of our processor units. We partner with Tyvek on a couple of CubeSats recently. So yeah, we do use commercial components. We've only developed things that do not exist commercially. So the deep space transponder we developed, the reflect array antennas we developed, are just things we were not able to find around commercially.
Yeah, well, these are pretty much systems, right?
Mm-hmm.
But I'm talking really component level. So whether you go to COTS components for these, and actually a couple of years ago I've heard that JPL is planning to have some database of components, of commercial components with flight heritage for CubeSats.
I'd stand up and say NASA is planning to do that. So NASA had a reliability workshop. All the NASA centers were interested or involved, and some of the industry players. And we started to talk about reliability standards and what we need for components for the future. I wouldn't say it's a solved problem, but we do use commercial parts if the lifetime isn't long. We also want to think about longer-lived CubeSats. If we're going to send them out to Saturn or Uranus, they need to survive.
Thank you.
Could you say more about the CubeSats associated with Europa Clipper? Because I thought that idea disappeared after the concept study y'all funded a couple of years ago.
No, I think it's still alive. So they funded 11 universities, academic institutes to do studies, and those studies terminated, but there is still mass margin. The project manager apparently still wants to fly a CubeSat. The program still wants to fly CubeSats. So watch this space. There have not been manifested so far, but there are some good ideas, and it's a strong possibility, let's say.
Is JPL intending to make the components they're developing for the space CubeSats commercially available, or is it?
We have. It's not as fast as we'd like. So the IRIS deep space transponder, for example, you can now purchase from a Space Dynamics lab in Utah, subject to normal ITAR rules, etc. And we hope to do the same thing to other components as well. But typically what would have to happen is that a US company would come to us and license it, and then it's open for purchase.
Okay, well, thank you very much. Thank you.